Hello and welcome to this presentation related to latent heat. This presentation builds on a previous presentation related to the heat energy required to change the temperature of a particular substance, either increasing its temperature or decreasing its temperature. But in this presentation we're going to consider the change of state and calculate the heat energy required to change the state from the equation Q is equal to m multiplied by h, where the symbol H relates to the specific latent heat of a particular substance. There will be two specific latent heats we'll consider, such as the latent heat of fusion, noted often as HF, and the latent heat of vaporization, often denoted as HV. We'll define these terms within the presentation. It is strongly encouraged that you've seen the previous presentation related to calculating energy required to change the temperature of a substance before reviewing this presentation. Here's an overview of the latent heat presentation. We commence with a very brief introduction, outlining the various states of a substance, defining the property specific latent heat, and stating relevant formulae required within the calculations to be undertaken. Essentially, this presentation builds on two examples from where we undertake exercises based on the examples and also some questions based on the examples. So example 1, we're asked to determine the heat energy Q and the power P required to raise 15 degrees C of water to steam at 100 degrees C. Example 2, we're asked to calculate the latent heat of fusion, denoted as HF you'll see, using a heat energy balance. Then we have the exercises. Exercise 1, we're asked to determine the heat energy Q required to raise ice at 0 degrees C to water at 6 degrees C. And exercise 2, we're asked to find the power P required for the process of exercise 1. So exercise 1 and 2 are essentially based on example 1. Exercise 3, we're asked to find the heat energy required to raise 20 degrees C water to 100 degrees C steam. Exercise 3 is based on example 1. And exercise 4, we're asked to calculate the latent heat of fusion, HF, given an experimental scenario, and that's very much like the solution required for example 2 above. The presentation concludes with some questions to consolidate your learning, and these questions are simply based on the examples and exercises shown previously. And here are the approximate start times related to the various sections contained within the presentation to hopefully aid your ease of access through the presentation, but please note they are only approximate start times, often rounded to the nearest minute. Let's consider the state of a substance. So a substance can exist in 3 states, or sometimes termed phases, and these are the solid, the liquid, and the gaseous, or sometimes termed the vapor phase. So the state of a substance depends on its temperature and pressure. So for example, water at atmospheric pressure is solid at temperatures below 0 degrees C, is liquid between 0 degrees C and 100 degrees C, and is vapor or in the gaseous state, sometimes referred to as steam, above 100 degrees C. Let's consider change of state. So when heat energy, usually symbol Q, is absorbed by a substance and there is no rise in temperature or pressure, the substance is changing its state. The quantity of heat energy required for a change of state to occur depends upon its mass and specific latent heat, that's sometimes referred to as specific enthalpy, of the substance and the pressure. But note the effect of pressure will not be considered within this presentation. Change of state continued. Here's a temperature versus energy diagram for water, and this is considered to be at standard atmospheric pressure. We're showing the temperature here in degrees C and heat energy as the unit of the joule. So essentially what happens here on the horizontal axis, heat energy is being supplied to the substance, and on the vertical axis we show the resulting change in temperature. So if we now consider our temperature against heat energy diagram, we can see that the ice starts at a negative value of temperature, usually termed a minus value. So this is the solid state of the ice. If we now apply heat energy to the ice, we notice that the ice will now start to increase its temperature. This part of the diagram is termed sensible heat. Sensible heat shows a change in temperature. If we continue to input heat energy to the block of ice, we now notice there is no change in temperature, but what we have now is a change of state. This is termed the latent heat part of the diagram, and you'll see very soon we need to use the latent heat of fusion, or HF, when calculating the heat energy required to change the state from a solid to a liquid. If we now continue to input heat energy into our water, we notice the water changes its temperature. Again, this is referred to as sensible heat. As we input heat energy to our substance, we see a rise in temperature. And of course, this is the liquid state now of the water. Once the water is at 100 degrees C, and we continue to input energy into the water, we now find there is no change in temperature. Again, this is referred to as the latent heat phase of the diagram. What we find now is we have a change of state from the liquid to the gaseous, or to steam. So you'll see we will need to use what's termed the latent heat of vaporization property, HV, when calculating the heat energy to change state from liquid to gas. So essentially in this presentation we're going to calculate the heat energy required to change temperature, which relates to the previous presentation, and also now to change state. Let's define the specific latent heat, or specific enthalpy, of fusion, usually denoted by the symbol H suffix F. So definition: the specific latent heat of fusion, HF, is the quantity of heat energy required to change unit mass of a substance from a solid state to a liquid state at constant pressure and temperature. For example, at atmospheric pressure, to change 1 kilogram of ice at 0 degrees C into water requires 335 kilojoules of heat energy, although the temperature remains constant. So specific latent heat of fusion for ice, HF, is 335 kilojoules per kilogram, or HF can be stated as 335,000 joules per kilogram. Note the freezing point is defined as the temperature at which any substance changes from a solid state to a liquid state. So for example, lead starts to solidify at 327 degrees C, thus the freezing point of lead is 327 degrees C. Let's consider specific latent heat, specific enthalpy of vaporization, usually denoted as H suffix V. So definition: the specific latent heat of vaporization, HV, is the quantity of heat energy required to change a unit mass of a substance, this time from a liquid state to a gaseous state at constant temperature and pressure. So for example, at atmospheric pressure, to change 1 kilogram of water at 100 degrees C into steam at 100 degrees C requires 2,256.7 kilojoules of heat energy. Again, during this phase, the temperature remains constant. So the specific latent heat of vaporization of water, HV, is 2,260 kilojoules per kilogram, or HV is 2,260 times 10 to the 3 joules per kilogram. The boiling point is defined as the temperature at which any substance changes from a liquid state to a gaseous state. So for example, at atmospheric pressure, ammonia starts to vaporize at a temperature of minus 33.4 degrees C. Thus the boiling point of ammonia is minus 33.4 degrees C. And note that's 33.4 degrees C below the freezing point of water. Table 1 here shows typical values of specific latent heat. So we have specific latent heat of fusion shown here. That's changing a substance from solid to liquid. Note these values are stated in terms of kilojoules per kilogram. And we have specific latent heat of vaporization. This is associated with a liquid to gas change of state. And again, these values are in kilojoules per kilogram. I have also included the specific heat capacity values denoted as lowercase c. These are from our previous presentation. And notice the unit is a joule per kilogram per K or per C. Just take note here that latent heats are often expressed in terms of kilojoules. So do be careful when extracting the information from the question. I find sometimes students forget the kilo prefix on the specific latent heat values. Here the heat energy formulae we'll be using within our calculations. First of all, the heat energy required to change temperature. This was reviewed in more detail in the previous presentation. So in this case, the Q to change temperature is equal to M multiplied by C multiplied by delta T. As always, heat energy is in joules, where M is the mass in kilograms, C is the specific heat capacity. That can be stated as joules per kilogram per K or joules per kilogram per degree C. And delta T is the change in temperature, and that's stated in K or degree C. Heat energy formulae continued. Let's consider the heat energy now required to change state. Firstly, from a solid to a liquid, the formula is Q is equal to M multiplied by HF, and again the heat energy is in terms of joules. And from a liquid to a gas, the heat energy required is again the mass multiplied by HV, joule. So here M is the mass, again in kilograms, and symbol H relates to the latent heat, which is in joules per kilogram or joules kilogram to -1. Heat energy formulae continued. We will also make use of the power formula. We've used this in previous presentations. Power is equal to the heat energy required divided by the time taken. And power has the SI unit of the watt. Q is heat energy, unit the joule. And note lowercase t is the time taken, and that should be in seconds. So let's now review some examples. Here's example 1. We have to determine how much heat energy is required to change 25 kilograms of water at 15 degrees C into dry steam at 100 degrees C. We're allowed to assume for water the specific latent heat of vaporization is 2,260 kilojoules per kilogram, and the specific heat capacity of water is 4,186 joules per kilogram per K. If the heat is supplied in 1.5 minutes, we've got to determine the power required for this process. Now within these solutions, I would always encourage you, where appropriate, to draw a temperature versus heat energy diagram. And that's what's shown here. Temperature on the vertical axis in degrees C and heat energy Q in joules on the horizontal axis. As an engineer, I like visual representations wherever possible, so I'm trying to extract the information from example 1 here and display it in a visual form that I can relate to when generating my solution. So essentially from the question, we have 25 kilograms of water at 15 degrees C. We're going to apply some heat energy to raise the temperature from 15 degrees C to 100 degrees C. So that's water at 100 degrees C. And then we're going to apply further heat energy, but this time we're going to change the state from water at 100 degrees C to dry steam at 100 degrees C. Extract the information from the question. The mass of the water M is 25 kilograms. the change in temperature, delta T. Remember, that's always the final temperature minus the initial temperature. So in this case, that's 100 degrees C minus 15 degrees C. So change in temperature is 85 degrees C. We're given the specific heat capacity of the water, simple C here, 4,186 joules per kilogram per K. And we're also given the specific latent heat of vaporization, HV. Notice that's in terms of kilojoules in the question. So I'm going to write that without the prefix. So that's 2,260 times 10 to the 3 joules per kilogram. The time taken, lowercase t, is 1.5 minutes. I converted that straight away into seconds. So that's 90 seconds. So there's the information extracted from example 1. Example 1, solution continued. So we're now going to find the heat energy Q required to undertake this process. So on the left hand side of my equation, I have the quantity of heat energy required, symbol Q. And on the right hand side of the equation, I state my calculation. I need to know the heat energy required to raise the temperature of the water by 85 degrees C. That's the sensible heat. And I need to also calculate the heat energy to change the water into steam. That's the latent heat. So in simple form, on the left hand side I have Q, total heat energy required, and that's equal to what I've termed Q delta T added to QV. So Q delta T is simply M multiplied by C multiplied by the change in temperature, and QV is the M multiplied by HV. That's the specific latent heat of vaporization in this case. All I do now is insert the values. So the mass is 25 kilograms. The specific heat capacity is 4,186 joules per kilogram per degree C. And the change in temperature is 85 degrees C. And to find the latent heat required, that's the mass, 25 kilograms, multiplied by the specific latent heat of vaporization, which is 2,260 times 10 to the 3 joules per kilogram. Calculating the Q delta T, calculating the QV. I calculate the total heat energy required as 65.4 times 10 to the 6 joules, or of course that's 65.4 megajoules. That's the heat energy required to be input to our system. So this heat energy now converts 25 kilograms of water at 15 degrees C through the temperature rise to 100 degrees C water. That's the Q is equal to MC delta T calculation. And this energy also changes the state of the 100 degrees C water, converting it to dry steam at 100 degrees C. That's the Q is equal to MHV calculation. Example 1, continued. We're also asked to calculate the power required, capital P. We know the formula for power is equal to the energy transferred, that's Q, divided by the time taken, T. So evaluating the power is equal to the energy calculated on the previous slide, divided by the time taken, 90 seconds. So essentially our power works out to be approximately 726.7 kilowatts. So here's the solution for example 1. Here's example 2. In an experiment to determine the specific latent heat of ice, 11 grams of ice at 0 degrees C was added to 120 grams of water at 30 degrees C. The final temperature of the water was 20 degrees C. We've got to calculate the experimental specific latent heat of ice. This would be the specific latent heat of fusion, HF. So as always, let's try and extract the information from the question and draw appropriate diagrams as required. So essentially we have a cube of ice, 11 grams at 0 degrees C, and we place that into a 120 gram tank of water, which is at 30 degrees C. This is termed the initial state. Sometime later, the ice has now melted, become liquid, and the tank of water has now reduced its temperature to 20 degrees C as the final state. So that's the experimental scenario we're considering. As always, I suggest we sketch a temperature versus heat energy diagram. So temperature here, degrees C, heat energy here Q in joules. And essentially what happens here is the 120 grams of water gives up some energy that's used to change the state of the small 11 gram block of ice, and then to raise the temperature of the 11 grams of what will be water to 20 degrees C. So on the temperature energy diagram here, we have our 120 gram tank of water initially at 30 degrees C, and over time the 120 grams of water reduces its temperature from 30 degrees C to 20 degrees. It's not changed its state. It was a liquid state at 30 degrees C, it's a liquid state at 20 degrees C, but it has changed its temperature, so it has given up heat energy. Conversely, the 11 grams of ice uses some of the heat energy given up by the 120 grams of water to initially change the state of the ice from 0 degrees C ice to 0 degrees C water. Now effectively, in this model we have 11 grams of water. And then heat energy from the 120 grams of water is used to raise the temperature of the now 11 grams of water to the 20 degrees C final state of the tank. I'm not sure if this diagram is helping you with your understanding, but essentially I'm trying to say as the 120 grams of water cools 10 degrees C, the energy given up by the water is used to change the state of the 11 grams of ice to 11 grams of water, and then change the temperature of the 11 grams of water to the common temperature of the water in the tank, 20 degrees C. So you'll see on the next slide we're going to use an energy balance to determine the value of HF. Example 2 continued. The mass of the ice is 11 grams, I've converted that immediately into kilograms, and the mass of the water in the tank, 120 grams, again converted into kilograms. Now note the temperature fall of the 120 grams of water in the tank, labelled it as delta T1 here, is the final temperature TF, 20 degrees C, minus the initial temperature of the water at 30 degrees C. So the temperature fall is actually 10 degrees C for the 120 grams of water. Conversely, the temperature rise of the 11 grams of ice, I've labelled that as delta T2 here, again it's TF minus TI, the final temperature of the 11 grams of ice is actually 20 degrees C when it's converted to water, and the initial temperature of the ice was 0. So the temperature rise of the ice was 20 degrees C. The specific heat capacity for water, symbol C here, is approximately 4,200 joules per kilogram per K. Example 2 continued. So here's the energy balance. We've reviewed energy balances in previous presentations related to mechanical energy, considering work done, potential and kinetic energies, and how we transfer energy from one form to another. So it's the same kind of approach here. On the left-hand side of the equation, we're going to consider the heat loss by the cooling of the 120 grams of water, and how that heat is given up by the 120 grams of water is then gained by the 11 grams of ice, and will change the state of the 11 grams of ice into water, and then raise the 11 grams of water in temperature. So in simple form, the heat energy lost by the 120 grams of water cooling, Q, is equal to the heat energy required to change the state of the 11 grams of ice, QF, added to the heat energy required to then raise the 11 grams of water in temperature. Inserting the formulae, on the left-hand side we have the MC and delta T1 equation, where the mass of the water in the tank is 0.12 kilograms. Specific heat capacity assumed to be 4,200 joules per kilogram per K, and the change in temperature is 10 degrees C. Now notice I actually calculated delta T1 as negative 10 degrees C, but in the calculation it's stated as positive 10, and that's because of the energy balance, because I have the cooling on the left hand side and the heat gained on the right hand side. This energy balance accounts for the loss of heat energy without me having to put the actual negative 10 degrees C in the calculation. If I had equated the equation to 0, which of course I could have done, because as we know energy is neither created nor destroyed, it's merely changed in form, then I would have had to put the negative 10 into that equation. But because I'm equating the heat loss with the heat gained, I do not need the negative 10 for delta T1. On the right hand side of the equation, QF is the mass of the ice multiplied by the specific latent heat for the ice. We know the mass of the ice is 11 grams, that's in kilograms here. Specific latent heat of fusion we're trying to find, so that's HF. The calculated change in temperature of the 11 grams of ice, that's MC in delta T2 here. So again, mass of the ice in kilograms, specific heat of water, 4,200, and the change in temperature of the 11 grams of water now is 20 degrees C. Essentially, the rest of the calculation is basically arithmetic, making sure we rearrange the equation for HF. And so the latent heat of fusion, HF, calculates to be approximately 374.2 kilojoules per kilogram. So that's how we'd undertake an experiment to try and find HF. We're obviously making an assumption here that there is no heat loss into the atmosphere or into the actual container storing 120 grams of water. So now I've shown you two examples that underpin basically the exercises that are going to follow. So I suggest you use the examples 1 and 2 as required when solving the following problems. So here's exercise 1. We're asked to determine the quantity of heat energy required to change 5 kilograms of ice at a temperature of 0 degrees C into water at a temperature of 6 degrees C. We can assume the specific heat capacity of water is 4,200 joules per kilogram per degree C. The specific latent heat of fusion of ice is 335 kilojoules per kilogram. The answer is shown in the bracket here. So I'd encourage you to start the presentation and attempt exercise 1. The solution is based on example 1, only in this case we're not changing the state of the water from liquid to vapour, we're changing it from ice to liquid. Exercise 1, commencement of the solution. As always, I would encourage you to initially sketch a temperature versus heat energy diagram. My sketch shown here. On the vertical axis, temperature in degrees C. Horizontal axis, heat energy Q in joules. And from the question, in this case, we have a change of state from 0 degrees C ice, change of state. And then we change the water in temperature from 0 degrees C to 6 degrees C. So in terms of energy calculations, we need to find the energy required to change the state. Q is equal to mHF, and the Q required to change the temperature, Q is equal to mc delta T. I'll let you review this solution at your own pace. It's based on the solution for example 1. Just make sure you calculate the change in temperature correctly. Be careful with the specific latent heat of fusion for ice, stated here. It's in kilojoules in the question, so I've stated HF in terms of joules here. So it's 335 times 10 to the 3 joules per kilogram. Students sometimes forget the kilo prefix, often stated with specific latent heats. Exercise 1, solution continued. So we're now going to calculate the heat energy required, symbol Q. So left hand side is Q. On the right hand side we have to calculate the heat energy required to change the state and the heat energy required to change the temperature. So first Q, QF, is calculated from the formula M multiplied by HF. We're given the mass in the question. We're given the HF in the question. We can evaluate the heat energy QF, and then we can calculate the heat energy to change the temperature. I've called that Q delta T here for reference. Formula is MC delta T. Again, we're given the mass, we're given the C value, and we know the change in temperature is 6 degrees C. So we can evaluate Q delta T. Simply add in the values. The total heat energy required, Q, is approximately 1.8 megajoules. Here's exercise 2. It's actually a continuation of the problem in exercise 1. It's based on the latter part of example 1. So we're given in this question the time taken to change the ice to water at 6 degrees C was 30 minutes. We've got to calculate the power required. They've given us the equation for power. P is equal to the energy transferred, that's Q from exercise 1, divided by the time taken given in the question. Answer for power is shown in the bracket here. I'd encourage you to stop the presentation and attempt exercise 2, but a calculation is shown on the following slide. Exercise 2, here's the solution. Just note that the time taken is stated in 30 minutes in the question. We need to convert that into seconds, so 30 multiplied by 60 is 1800 seconds. The heat energy required was calculated in exercise 1, 1.8 times 10 to the 6 joules. So we can now calculate the power, simply Q divided by T. So the power in this case is 1 kilowatt. Exercise 3, we're asked to determine the quantity of heat energy required to convert 8 kilograms of water at 20 degrees C. We're given the specific heat capacity for water. We're given the specific latent heat of vaporization for water. We're also given the time taken for the process is 1 hour. So we have to calculate the power required. The answers are shown in the bracket. Again, this exercise is based very much on example 1. So I'd encourage you to stop the presentation and attempt exercise 3 using example 1 as a template. Exercise 3, full solution. Again, as always, I encourage you to sketch a temperature versus heat energy diagram. My temperature degrees C, my heat energy Q, and I've sketched out the process changing 20 degrees C water to 100 degrees C water, and then changing the state of the water to steam. That's steam at 100 degrees C. So again, two energies to calculate: the energy required to change temperature, Q equals mc delta T, the energy required to change state, Q equals mHV in this case. Just notice in the question, the specific heat capacity of water is stated actually in kilojoules this time. So specific heat capacity C is actually 4,200 joules per kilogram per degree C. The latent heat of vaporization for the water is stated in kilojoules per kilogram, but that's convention. So HV 2,260 times 10 to the 3 joules per kilogram. Note the time taken for the process is stated as 1 hour. So time taken T is actually 3,600 seconds. So here's the information extracted from exercise 3. And here's exercise 3 continued. Firstly, to find the heat energy Q is equal to the heat energy to change the temperature of the water added to the heat energy to change the state from water to steam. Just notice in this solution I've actually factorized on the mass M here. So just a slightly different layout to that used in the example 1. I'll let you undertake the calculations, but the quantity of heat energy required is 20.768 megajoules, and we can calculate the power required P from the equation Q divided by T. So inserting the values, the power required is approximately 5.77 kilowatts. Finally, exercise 4. This is based on example 2. Given a mass of 10 kilograms of ice at 0 degrees C is added to 100 kilograms of water at 32 degrees C. If the final temperature of the ice and the water was 21 degrees C, we've got to calculate the specific latent heat of ice, and we're given the specific heat capacity of water as 4.2 kilojoules per kilogram K. The answer is shown in the bracket here. I encourage you to start the presentation, attempt exercise 4. It's almost an identical solution to that of example 2, but I'll show you the full work solution on the following slides. So exercise 4, beginning of the solution. So in this scenario, 10.9 kilograms of ice at 0 degrees C is placed into 100 kilograms of water at 32 degrees C in a tank. So that's our before, our initial scenario. And sometime later, the entire contents is now in a state of water at 21 degrees C. That's the after or the final condition. As I say, solution for exercise 4 very similar to that of example 2. I'm going to let you work through a solution at your own pace here. In this case, the fall in the temperature of the 100 kilograms of water, delta T1, was minus 11 degrees C. The rise of the 10.9 kilograms of ice, delta T2, was 21 degrees C. Example 4, solution continued. So here's the energy balance again. Heat lost by the 100 kilograms of water cooling goes into heat gained by the 10.9 kilograms of ice, changing its state to water and then raising the 10.9 kilograms of water 21 degrees C. Again, I'm going to let you review the solution at your own pace. Just note again that delta T1 will be positive because of the energy balance we're using here. It is a minus 11 degrees temperature change. Just note here again that the delta T1 is positive 11 degrees, although it was calculated as negative 11. Because we're using an energy balance here, its value is positive 11 in the equation. Final answer for HF is approximately 336 kilojoules per kilogram. Again, use example 2 as the basis of your solution here. It's basically the same problem but with different numerical values. Finally, I'll leave you with some tutorial questions. Question 1 through to question 3 shown here, answers stated in the brackets. Here's table 1 for reference. Question 4 and question 5. Just note that question 5 has two changes of state here because we're converting ice 0 degrees C into steam at 100 degrees C. So here we have ice at 0 degrees C converted to water at 0 degrees C, so that's a latent heat problem. Then we have water at 0 degrees C converted to water at 100 degrees C, so that's an MC delta T problem. And then we have to convert the water at 100 degrees C into steam at 100 degrees C, so another latent heat problem. We're asked to find both the energy required and the power required. And finally, question 6 and question 7. Just note in question 7 there's a slight twist here in that we have to convert 9 kilograms of ice from minus 12 degrees C into steam at a temperature of 100 degrees C. So we're actually given the specific heat capacity of ice, something we haven't used before in any previous question, and that's 2093 joules per kilogram per K. The specific heat capacity of water is the same as we've used in previous questions. So I say a slight twist here because we will have to work out the energy required to raise 9 kilograms of ice at minus degrees C to 0 degrees C, so that's a MC delta T problem. Then we've got the change of state from ice to water, that's a latent heat problem. Then we've got to change water at 0 degrees C to water at 100 degrees C, so another MC delta T problem. And then finally we have to change the water at 100 degrees C into steam at 100 degrees C, so that's another latent heat problem. So a slightly more complicated process in question 7. Again, as always, I'd encourage you to sketch a time energy diagram to show the various stages of the process. Answers to the various questions are stated in the brackets here. So I hope this presentation has been of interest to you, and thank you for viewing.